In this video, we're going to start looking at differential equations. Now, we're going to find that they are very similar in terms of the way we solve them to what we had just done with regards to difference equations. So we're going to start with the homogeneous first-order linear differential equation. And we write it in this form here, a0 times the derivative of y, where y is a function of t, plus a1 y equals 0, and we assume an initial condition that at time 0 we have c0. So we form the equation in operator form as a0d plus a1 all times y of t equals 0. And we let b equal minus a1 over a0, so that the first derivative of y with respect to t, which we denote y with a dot over top, and we'll do the same for the second derivative, except we're going to put two dots on top, and we set y dot equal to by. Recall that if y is equal to k e to the bt, this implies that the first derivative of y with respect to t is equal to b times k e to the bt, which is simply ky. Upon setting t equal to 0, we then get y k e to the b times 0, and that means that e to the 0 is equal to 1, which means we get k, which is equal to c0 from the initial condition. The solution to this differential equation is simply y equals c0 e to the bt, where b is equal to minus a1 over a0. So let's assume that c0 is greater than 0. Then we have three cases to consider. First off, if b is greater than 0, then we'll find that because this is greater than 0, this b here, e is going to go e to the bt multiplied by c0 will explode as t goes to infinity. The second case is where b is equal to 0, so then it implies that y is equal to c0 for all values of t. The third case is that b is less than 0, so in that case y will decline to 0 as t goes to infinity, because this up here, this b, is less than 0. So these three cases can be illustrated in these three diagrams. The first one shows you that starting at c0, yt will explode as t goes to infinity. In the second case, b equals 0, and we find that c0 remains constant, or yt rather, is constant at c0 regardless of what value of t we choose. And the final one shows you that starting at c0, you decline towards 0, so yt falls towards 0 as t increases. Now assume that c0 is less than 0. So in other words, the initial condition, the starting condition, if you like, c0 is a negative number. So then we find that if b is positive, is greater than 0, y begins as a negative, and it approaches negative infinity as t approaches infinity. The second case is similar to that, or in this case, case 5, is similar to case 2, where b equals 0, in which case y is equal to the value of the constant, which in this case is negative, and that holds for all t as well. Finally, the sixth case is where b is less than 0, then y approaches 0 from below as t approaches infinity. And these three cases are shown here. The first case where we start at negative c0, or at c0, which is a negative value, and we see that it moves towards yt, decreases towards negative infinity as t goes to infinity. The second case, c0, it's constant across, and the third one, we begin at a negative number, c0, and it approaches the horizontal axes, y does, as t increases. The size of b determines if the time path of y will be explosive, constant, or diminishing. Again, recall that b is equal to minus a1 over a0, so that the nature of the time path is known from the parameters of a0 y dot plus a1 y equals 0. So we know the nature of the time path once we know a0 and a1, and those are given when we're ready to solve that particular problem. Second order differential equations. The standard one is given as a0 y double dot, so that's d squared y over dt squared plus a1 dy dt this one here, plus a2y equals 0. Written in operator form, we get a0d squared plus a1d plus a2 all multiplied by yt equal 0, which is the homogeneity condition, a homogeneous equation. So in this case, we let y equal e to the bt. Y dot then, taking the derivative of y, is equal to b e to the bt. And finally, the second derivative of y with respect to t is equal to b squared e to the bt. And we substitute that into equation 1. So we substitute each of these into equation 1. So that gives us a0b squared e to the bt plus a1b eb to the e to the bt plus a2 e to the bt. And we notice that we can factor out e to the bt, in which case we end up with a0b squared plus a1b plus a2, which is very familiar to us as an auxiliary or characteristic equation, except that with the auxiliary equation, we'll substitute an x for the b there and then find a solution to it. Notice that this is the same form as in the case of difference equations, and the approach to solving this kind of a problem is similar to the approach we used with difference equations. So we begin with that auxiliary equation by replacing b with x. So the auxiliary equation then has two roots, x1 and x2, and we need two initial conditions, but both have to be at time t equals 0. These initial conditions are needed to determine two constants, k1 and k2. So remember that x1 and x2 are determined from the auxiliary equation, and k1 and k2 are determined from the initial conditions. And with those initial conditions, both have that y is equal to k1e to the x1t and y equals k2e to the x2t. The general solution to the second order differential equation is given by equation 2. Y equals k1 e to the x1t plus k2 e to the x2t. If we take the first derivative of that, we get k1 x1 e to the x1t plus k2 x2 e to the x2t. Now we have initial conditions that y0 at time 0, in other words, y is equal to c0, and the first derivative of y at that time is c1. So if we put in t equals 0 here, then we get 0, and we're left, we get e to the 0, which gives us a 1. So we get k1 plus k2 is equal to c0. Then we take the derivative of this general solution, and we find that it's equal to k1 x1 e to the x1t plus k2 x2 e to the x2t. And again, we solve this at t equals 0, which means that this is a 1 and this is a 1, and we end up with x1 k1 plus x2 k2 equals this first condition, c1. So the second order equations with distinct roots, suppose that our auxiliary equation is then x squared minus 3x minus 10 equals 0. And we see how similar it is to the operator form of the equation. And we get that x1 minus 5 plus x2, x plus 2 equals 0. So x1 equals 5 and x2 equals minus 2 are solutions. Then using equation 2, we fill in that y is k1 e to the 5t plus k2 e to the minus 2t, where the 5 and the 2 are given by the first or the roots of the auxiliary equation. Then we use our initial conditions to construct k1 plus k2 equals 8, 5k1 minus 2k2 minus 2. That gives us, when we solve these two equations, k1 equals 2, k2 equals 6, and the final solution as a result is y equals 2 to the times e to the power 5t plus 6 e to the power minus 2t. Again, with a quadratic auxiliary equation, one can have multiple roots or complex conjugate roots. So let's look first at the second order equation with multiple roots. and let's look at this example. So the problem to solve is 2 times y double dot minus 28y dot plus 98y equals 0. 2d squared plus minus 28d plus 98 times yt equals 0 is our operator form of that equation, which implies that the auxiliary equation is 2x squared minus 28x plus 98 equal to 0. And that implies that we get these two roots, and the roots are x17, x27, and they're identical. Further, we're given initial conditions, y0, so at time t equals 0, y is 5. At t equals 0, the first derivative of y equals 1. So when we construct the equations as we did before to try and determine what k1 and k2 are, we find that we have an inconsistency. So k1 plus k2 is 5, and k1 plus k2 is 1 over 7. That's an inconsistency. So we need to alter equation 2 above as follows. So we take y of t equals k1e x1t plus k2 times t. We add this t here multiplied by e x to the t, x2 to the t. We find that x1 and x2 are 7 as before, and we now use the initial conditions. Now to find those for y dot is equal to derivative of y with respect to t. We see that it's equal to k1 x1 e to the x1t plus k2 x2t times e to the x2t plus this other term k2 e to the power x2t. Now if we have t equals 0, these terms e to the x1t, e to the x2t are equal to 1. So for the first one, we get that t equals 0, so that cancels out. And we get that k1 equals 5. In the second case, where we have dy dt equal to this term here is k1 x1, which is 7. If we plug in the values, we get 7k1 because of this 7 there, plus, well, if t is 0, this term cancels, so we're left with this term here, k2, but in this case, we don't have a 7 in front of it. We just have 7k1 plus k2 equals 1. Solving, we get k1 equal 5, which is obvious, and k2 in that case is minus 34. Then from equation 4, our final solution to this problem is y is equal to 5e to the 7t minus 34t times e to the 7t, which is equal to 5 minus 34t, all multiplied by e to the 7t. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.